In this episode of Woodlands on the Web, we'll be finishing up our discussion on AP Chemistry Unit 6, Thermochemistry. We'll be talking about Hess's law, enthalpy, and Gibbs free energy. So here we're going to be looking at enthalpy as being part of a multi-step reaction this time. And this should bring back memories of dealing with multi-step reactions in kinetics. The process is going to be very similar in that if we know the enthalpy of individual elementary steps within an overall mechanism, we'll be able to combine those together to talk about the enthalpy of the overall reaction. All right, in exercise 11, what we need to do first is figure out how are we going to get to this overall balanced equation using these elementary steps. Okay, so the main thing here is that we want to make sure that we have our reactants and our products on the correct side of the reaction. So first of all, I'm going to look at this first step, and we have H3BO3, which is our reactant, but notice we have 2 moles of that in the overall reaction. So I'm going to multiply my entire reaction, or reaction 1, by 2, which means that I'm going to be multiplying that step's enthalpy by 2. For the next reaction, I've got H2B4O7, and since that does not appear anywhere in my overall reaction, that ought to be an intermediate. Okay. Additionally, we're going to be looking at the fact that we're trying to make that work also with our third step. Okay, notice here that in our third step, we do have B2O3 as our product, and that does match the product side of our overall reaction. So in order to get my H2B4O7s to divide out or cancel out, actually in this case, we're actually going to want to reverse reaction 2. So we're going to use this as the reverse reaction, which means that our enthalpy is going to be the opposite sign. So we're going to multiply that by at least a negative, but we'll see that we're actually going to need to do something else. Okay, so let's look back at reaction 3. And we did identify B2O3 as being on the correct side, but notice that we have twice as much B2O3 in our written out elementary step. So I'm actually going to want to multiply this entire reaction by 1/2, which means I'm going to be taking 1/2 times 1/2 of that enthalpy. And in order to make these things divide out, that means I'm also going to have to multiply this by a 1/2 as well. Okay, I'll show out the steps with them converted here in just a second. But essentially, we're trying to see how we manipulate the equations to make them all overall add up to the overall reaction. And whatever manipulations we have to do those to our enthalpy values as well. So here I've written out my elementary reactions with those modifications that we made, just to show that this is going to come up to be the overall reaction. Okay, so we have 2 HBO2 on both sides of the reaction arrow. We also have 1/2 H2B4O7 on both sides of the reaction arrow. So now if we add up everything that's left, we're left with 2 H3BO3, B2O3, and we have 2 H2O plus 1/2 plus 1/2, giving me a total of 3 waters. Okay, and since that is going to equal my overall reaction that I was shown, then when I add up those values, as I mentioned, so I'm going to use negative 0.02 times 2. This negative 11.3 gets multiplied by negative 1/2, and 17.5 gets multiplied by 1/2. Add it all together, we end up with an overall heat of reaction of 14.36 kilojoules per mole. Now we're going to move on to talking about bond energies. So this is actually different than heat of formation that we've talked about before. The most important statement to catch here is that when you break bonds, that's an endothermic process, and when you form bonds, that's an exothermic process. So it takes energy to break bonds that already exist, and when a bond is formed, energy is released. Okay, When we do that, that means that if we're talking about endothermic, breaking old bonds is going to be a positive sign for our enthalpy, and the formation of our new bonds is going to be a negative sign for enthalpy. So relating this together for exercise 12, keep in mind here, these are not enthalpies of formation. This is referring to specifically the energy found within these bonds that are shown in between the atoms. Okay, so that's your chemical potential energy that's found in those specific substances. So in this case, if we're looking at our overall delta H, it's going to be the sum of our bond energies broken, which is going to be the bonds of our reactants, because that's what we're taking apart. So we'll have 432 kilojoules per mole plus 154 for our reactants. And you're going to subtract the bond energies that are formed. In this case, the HF bond energy is 565, but we form 2 moles of that. So we're going to multiply that value by 2. And when we do that, we get negative 544 kilojoules per mole. Okay, so this summary statement up here basically tells us, why do we even care what the enthalpy of a reaction is? That's because it's going to tell us whether or not heat was added or lost from the system. And I'd like to take that, and we'll talk about how this relates to some other things that we've observed in the past related to physical changes. Okay, so we've talked about our changes between different states of matter, and we've talked about how those processes are either involving an input or a release of energy. So endo or exothermic processes, not reactions in this case. Keep in mind that phase transitions and these physical changes are caused by overcoming the intermolecular forces that are involved in that substance, not talking about the actual bond breaking and forming themselves. We're talking about intermolecular forces there. Okay, so I'd like you to read over this portion. I'm not going to go into a lot of detail, but I would like you to read over it or go to the online notebook and read it again. The most important statements, though, from here are that you need to be very clear, again, that we are talking about, whoops, I didn't mean to squiggle. We're talking about changes in phases being altered IMFs. Okay, not altering chemical bonds, because otherwise you would be changing the identity of the substance. Okay, the other important statement is the more polar, the stronger the attractive forces. That's why we have those different types of intermolecular forces between those. Okay, phase transitions again involve in breaking or forming intermolecular forces between multiple particles. Okay, this also relates to phase diagrams or heating curves. So I would like you to take a moment, and if you would, it'd be best if you go to the online notebook and look at the questions, but I will try to scroll through them here in case that you're accessing this outside of my class so that you can see the questions. But again, I'm not really going to go over these because these were discussed way back in Unit 3 when we talked about intermolecular forces. The only change being that this particular question, number 7, is referring to the thing you identified in question 6. And we are going to finish up this discussion with Gibbs free energy. So Gibbs free energy is the amount of energy that is actually available to do chemical work. And it's going to be the enthalpy minus the temperature times the entropy. Okay, so we're basically talking about the total energy as it relates to the surroundings and the system. Okay, this chart is generally a pretty good one to know. It's often simplified to only including the delta H and the delta S, and I'm going to show you that in just a second. So this is the chart that you usually see, and it's a good summary chart to help you remember whether or not a reaction would be spontaneous. Basically, if you have a delta H less than 0, this is an exothermic process. Delta H greater than 0 would be an endothermic process. Entropy is the amount of disorder in a system, and the universe tends towards disorder. So if the universe is becoming more disorderly, then that is going to be the way that things would normally happen. If the delta S is negative, then it's going to be more orderly or less disorderly. So basically, if you're talking about something being always spontaneous, that's because you're talking about an exothermic process that's tending towards disorder. Something that is never spontaneous is when you have an endothermic process, so it's requiring the input of energy because of heat, and it's also requiring an input of energy in order to organize. So that's why those are never spontaneous. And then the other two, it depends on the temperature, because the Gibbs free energy formula does depend on how temperature is relating to entropy. So let's say we have a reaction that contains the following conditions. So it's an exothermic reaction. It's happening at roughly, well, actually in this case, it's happening at 0 degrees Celsius. And it is also going to be tending towards disorder. Okay, so because delta S is positive. So if I'm actually plugging it into my equation, then plugging those values in, just as they're listed essentially, I'm going to get a delta G value of negative 114 kilojoules per mole. Using yet another spontaneity chart, this helps us decide what type of reaction it's going to be. So if delta G is negative, then it's going to be spontaneous at any temperature. And so therefore, because this is a negative value, we can say that this is always a spontaneous reaction, even though I know there's no reaction shown. Finally, in our last example, I'd like us to tie enthalpy and entropy together with heat of formation. So if we're talking about the Haber process, we're talking about nitrogen and hydrogen combining to make ammonia. So we have N2 plus H2 making NH3. Technically, that's in equilibrium, but it's fine for right now, okay, because we mainly just need our coefficients. Okay, so I'm going to pull the heat of formation values from a reference as well as the entropy values. So these are all things that you can look up as physical constants. So these are the constants that you need. Keep in mind, because nitrogen and hydrogen are in their natural state or their stable state, they have an enthalpy of formation of 0. So I'd like you to challenge yourself and see if you can find the delta H of this reaction, the delta S of this reaction, which is the same idea of products minus reactants, and try to find the delta G of the reaction, assuming that this is at standard conditions. So taking all of that into account carefully, pause the video and see what you can do before you move on. So these are the answers that I got mathematically. Okay, first finding the delta H value. So I'm using the NH3 times 2 minus the zeros, which gives me negative 92.22 kilojoules. So I know that that is an exothermic reaction, therefore it is favorable in the case of exothermic things. Okay, looking at delta S, I have something going from, I can actually look at just the equation itself. I have two separate things organizing to make one single compound. So this is going to be considered a decrease in disorder, or you could say that it's becoming more organized. Okay, so this is an unfavorable process. Okay, the actual value associated with that would be negative 198.75. So again, I'm using my values that I looked up and multiplying by their coefficients. Okay, I need that to plug into my Gibbs free energy equation. So I have my delta H minus, I said standard conditions, which means 25 degrees Celsius. In kelvins, that's 298 kelvins. And the main thing here that I changed, because I'm calculating kilojoules in this case, is I converted this negative 198.75 joules to kilojoules here in order to get negative 32.99 kilojoules overall. So again, if we refer back to this video or this image, we see that we had an exothermic process and we had unfavorable entropy. So that means that that reaction is spontaneous at low temperature.